Okay, good afternoon, everyone. My name is Saqib Hassan, and this video is a first in a series of videos where I will be going over chapter 13, Reacting Mixtures and Combustion from the Moran book. So without further ado, let's get into it. So in this first video, we will first be introducing the concept of combustion. Now, what is combustion, really? Now, combustion is any chemical reaction where you have a reactant plus an oxidizer where the both of them react to give you certain combustion products plus an enormous amount of energy. So any reaction that looks like this is what we would call a combustion reaction. Now, why are combustion reactions important to us? Okay, where's my razor? So, why are combustion reactions so important for us? So, as we know, in any thermodynamic cycle, you need to have what's called a hot reservoir at some higher temperature TH and a cold reservoir at some lower temperature TC. And ideally, you would have some sort of a heat engine between these two. And as heat is being transferred across these two uh, thermodynamic reservoirs, essentially, you get a work output. Now, this work is extremely important for us because this is the work that you're getting in, let's say, your combustion engines in your car or your turbine in your power plants. So this workout essentially runs the world if you think about it. Now, in in practice, we don't really have a magical hot reservoir from which you can tap into and then get a bunch of energy. Okay, so we don't have that. So instead, what you need to do is you need to generate the heat, right? You need to generate the heat by some sort of external source. Now, there's many ways of generating heat. But one of the ways that you can generate heat is by combustion. And in fact, it happens to be one of the cheapest forms of creating, well, not creating, but getting out heat energy. So what do we use for our reacting? So we primarily use what's called hydrocarbons. Okay, so when you're thinking of fossil fuels, you're thinking about hydrocarbons. You're thinking about, let's say, methane or octane or any number of different carbon hydrogen combinations, you know? So the main constituents here are going to be carbon and hydrogen. And we will later see that these fuels tend to have a variety of different compounds, and they can include other elements like nitrogen, sulfur, and even oxygen itself. So we essentially react these hydrocarbons with the most abundant oxidizer that we have, which is oxygen in the atmosphere. And then you get CO2 as well as water as your combustion products, as your primary combustion products. Of course, if you have these elements, they will also, well, not oxygen itself, but if you have nitrogen and sulfur, they will react to form all sorts of nitrous oxides and sulfur oxides. So the next part where I want to draw your attention to is the type of combustions that you can have. Well, there's two types of combustions that you can have. You can have what is called a complete combustion, or you could have an incomplete combustion. Now, what is a complete combustion? So when you have a reaction, for instance, let's say you have CH4, right? And it reacts with oxygen and it forms carbon dioxide as well as water. So in this reaction, you could say that this is a complete reaction because all of the carbon and all of the hydrogen is reacting with the oxygen to form carbon dioxide and water, respectively. And the same has been stated here, as you can see. However, if you have sulfur, if in a complete reaction, all of it is burned to form sulfur dioxide. And if you have other combustible elements, for instance, nitrogen, they must also be fully oxidized. However, if under some circumstance these conditions are not met, then you have what's called an incomplete combustion. And usually in an incomplete combustion, you will have products such as carbon soot, or which is primarily graphite, I believe. So you will have carbon soot as well as carbon monoxide, which is a poisonous gas. And the reason why this matters is because in in our daily lives, this is usually what is happening. We usually don't get a complete reaction. So it is important for us to study incomplete combustions because it allows us to know how much energy we're actually getting out of our combustion reactions. So in our next part, we will be looking at a balanced reaction equation. So what is this balancing of a chemical reaction? We know from basic chemistry that you can essentially use the mass balance principle to find the ratio of how the ratios between these reactants and how they're reacting to then also find the ratios between the products. Now, what do I mean by ratios? What I mean by ratios is that, for instance, for every 1 mole of CH4 or methane, you will have, as we've found here, 2 moles of oxygen. Since A will be equal to 2, you can show, well, I mean, I don't know why they didn't show it here, but A here is equal to 2. Oh, as you can see, A is equal to 2. They did show it. So for every 1 mole of methane, you have 2 moles of oxygen. So it's a 1 to 2 ratio between methane and oxygen reacting to form 1 mole of carbon dioxide and 2 moles of water. So there's a 1 to 2 ratio between uh, the methane and the water, and then a 1 to 1 ratio between the methane and the carbon dioxide. Now, what is meant by moles here? Now, moles is essentially a unit. Well, it's not technically, it isn't a unit. It's more so a quantity that represents, I believe, about 6.02 times 10 to the power of 26. It's either 26 or 23. I believe either of the two values, but I think pretty sure it's 10 to the power of 26. So moles just happens to mean 6.02 times 10 to the power of 26 of something. Just like how, let's say, a dozen just happens to mean 12 of something, right? And you can think of moles as just representing this number of something. And here we're representing the number of molecules. So if we're talking about 1 mole of methane, let's say, you have this many uh, well, molecules of methane. Actually, I was wrong here. It should not be 26. It should actually be uh, 23. So I was wrong here. It should be 10 to the power of 23. Okay. So as you can see, you can use this mass balance or conservation of mass principle because the amount of carbon on this side should be equal to the amount of carbon on that side. And the amount of oxygen and hydrogen on this side should also be equal to the amount of oxygen and hydrogen on the other side. So you can use these principles to then use algebra to find these values of A, B, C, and if you have a larger reaction, you can find it for other compounds as well. So this is useful because it lets you know, okay, the ratios between the reactants and the products, which will be useful later on when we're performing calculations. Okay, so let me clear all this. All right. So the next part is the modeling of the combustion air. Now here, this is a bit interesting because we know air consists mostly of nitrogen. So if I drew a rough pie chart, so it's going to be mostly nitrogen, 1/5 oxygen, so a substantial amount, and then just a little tiny bit of other things. Okay. Now, for the simplification of our analysis, we say, okay, this extra stuff is also oxygen. So we actually ignore essentially this extra bit and we just treat it as oxygen. And again, you will see that ultimately the ratio comes to 21% oxygen to 79% nitrogen on a molar basis. And a molar basis is also a volumetric basis, if you recall Avogadro's principle, which states that at a given pressure and temperature, the number of moles of a gaseous substance or two gaseous substance will be the same. So using this, we can now find the mole ratio between oxygen and nitrogen. So for every 1 mole of oxygen, you will you will find that you're taking in 3.76 moles of nitrogen into your system. Now, okay, we also know for a fact that nitrogen happens to be extremely chemically inert, so it won't react in most circumstances. However, we still take it into account because when you're pulling in oxygen into your system, let's say, right? You have your engine here. You're pulling in oxygen clearly for the combustion, but you're also pulling in a large amount of nitrogen. So when you're calculating, let's say, the mass flow rate of of air, you can't you can't just work with oxygen. You also have to work with nitrogen, which is why we're including nitrogen in our chemical equations, essentially. All right, let me clear all of this. Oh, okay. So the other thing that I want to draw your attention to is this thing about moist air. So we know that air also naturally tends to have a bit of moisture, a bit of water vapor. Now, in some analyses, we may include water vapor, okay, in our chemical reaction. So we should be aware of that. So I think I will end this particular video here. In the next video, I will be looking at some of the other things like air fuel ratio and whatnot. So for now, I'll end it here. Goodbye.